Okay, so in this problem, we're told a fabric used in air-inflated structures is subjected to a biaxial loading that results in normal stresses sigma x equal to 120 megapascals and sigma z equals 160 megapascals. Knowing that the properties of the fabric can be approximated as E equals 87 gigapascals and nu equals 0.34, determine the change in length of A, side AB, B, side BC, and C, diagonal AC. So I went ahead and drew the figure here. So what we have is this sheet, right? And it's going to be along this X and Z axis. And so we know that the Y axis is going to be pointing up directly through it. So this is a 3D figure. And then we know what we're going to have is these biaxial loading, right? So we have these forces that are going to be acting this way and this way. Notice this one is parallel to the x-axis, and then these are parallel to the z-axis. And so we're given the values of the stress in the x direction and the stress in the z direction, which let's go ahead and write that down. So let's write that down, given. So we're told these two values in the problem, so it's always good to write those down. So sigma x, and this is supposed to be sigma z, are equal to 120 megapascals and then 160 megapascals. So these are the stress in the x and z direction. And then another thing we should write down is the stress in the y. Now notice that there are no forces or loading in the y direction, therefore the value of it is just going to be 0. Since there's no loading in that direction, it's just going to be 0. So this is going to be helpful for later on, but it's important to recognize that. So we're given that, and then we're also given two other values. We're given E, which is the elastic modulus, right, which is going to be 87 gigapascals. And then we're also given Poisson's ratio nu. Let's go ahead and write that down too. So nu is a value of 0.34. So these are all the values we're going to need to actually go ahead and solve this problem. And yeah, so now let's go ahead and talk about what they're asking for and how we're going to solve it. So what they want us to find is the change in length of each of these sides. So we're basically going to find out how much this side, we'll just call it length AB, for the first part at least, is going to change. So we want to know how much it's going to either increase or decrease. And then we're also going to want to know side BC, which would be this. So we're going to find out how much this one is going to change. And then also this one. So just both of these. And then finally, we're going to find how much it changes in the diagonal, which is along here. So how long it's going to basically change this way. So let's go ahead and get into it. So the way we're going to solve for this is by using the strain formula. So you should know this by now, that strain is equal to the change in length over the initial length. You can just call it L0. So this is the formula for strain, but what we're going to be doing is breaking them down into each direction based on certain formulas. So let's go ahead and start with A, and I'm going to explain to you how this works. So there's different formulas for strain depending on the direction you're going. So what we have here is epsilon x, epsilon y, and epsilon z. And they basically just represent the strain in each direction as a result of the stresses. So let's start off with the x direction. So if you look in your textbook, you're going to find the formulas for the strain here in each direction. I'm just going to go ahead and write it down for you. So the strain in the x, which keep in mind when I'm referring to the x, I'm talking about the strain in this direction. So essentially the strain in the x is the strain of AB, which is something you have to realize to do this. So basically, the strain in the x is going to be equal to sigma x over E. And so there's different forms of this formula, but it's important just to write down the base. It's going to be simplified. Minus sigma y over E minus nu sigma z over E. Let me make sure you can see that. But yeah, so this is the formula for the strain in the x direction. Now, the thing that's important to notice here is there is no stress in the y. So it actually simplifies this problem a bit. So this term is 0. Obviously, this is going to cancel out. So you're really just left with these two terms. And then I'm going to simplify them a bit further. So sigma x, or sorry, not sigma, epsilon x is equal to 1 over e. And then we have sigma x minus nu sigma z. So if you look right here, this is going to be the formula. All I did was factor out the e right here, and then I just moved these terms. I just factored it out. And yeah, it's really just a matter of plugging it in now. So plugging in our values, let's go ahead and do that. So 1 over, let's see what E is. So E is 87 gigapascals, right? So giga is 10 to the 9. So let's go ahead and write that. 87 times 10 to the 9, right? And then sigma x is 120 megapascal, so times 10 to the 6 minus nu, which is 0.34, times 160 times 10 to the 6 again. So this right here is right, all the values plugged in. So this should give us sigma, or sorry, I keep saying sigma, epsilon x, right, our strain. And then when you do this, you're going to get a value of 7.54 times 10 to the minus 4. And then keep in mind our units here. So since we converted this to pascals, this is actually going to be in meters. So keep that in mind. But yeah, so this is going to be your strain in the x. And then now that we have this, how are we going to use the strain in order to get our, right, what they're asking for is the change in length, right? We're going to go back to this formula right here. So looking at this, you should recognize we can solve for the change in length here, change in length, since we know this strain value. And we know the initial length, they give it to us, right? So keep in mind, we're doing this for initially side AB, which is this side right here. So we just solved for the strain in the x, which we agreed was the strain in the AB. And then we know the initial length in the AB, right? This length, what is it? It's 100 millimeters. So it's really just a matter of plugging it into this formula here. So let's go ahead and do that. So we have EX equals, we'll call it change in length AB over the initial length in AB. So we want the change in length. So it's going to be equal to the initial length, right, we'll call it LAB, multiplied by, right, our strain. So the initial length was 100 millimeters, which we want it in meters since this value right here is in meters. So 100 millimeters, 2 meters, you should know that conversion is just 0.1, right? So 0.1, and then you're going to multiply that value by 7.54 times 10 to the minus 4. So go ahead and do that. And then, yeah, so what you're going to get is, keep in mind, this is going to be in meters. So all you're doing is multiplying it by 0.1. So we can just rewrite it as 7.54 times 10 to the minus 5 meters. And I think this answer is easier to be seen as millimeters because, right, we just want to convert it to make it look nicer. So this value right here is, right, you would just multiply it by 1,000 to get it in millimeters. I'm not going to show you how to do that, but it's just 0.0754 millimeters. So this is going to be your answer to A at least. So we found the change in length of side AB. So we're basically just going to go ahead and repeat this process for BC. So let's go ahead and do that now. Yeah, so what we want to do now is keep in mind we just, I'm going to do it over here. So keep in mind we just did it for e to the, or sorry, epsilon to the x, since we were doing AB, But now that we're doing BC, notice it's along the z, or it's parallel to the z. So we're going to be doing this right here. So let's go ahead and write down the formula. So the quick trick to these is just to notice that these variables are going to stay the same, right? So notice this one right here, I'm going to write sigma z over e, since the one I'm choosing to do it at the side is that one, right? And then we just minus and then just do the other two. So we have nu sigma x over e minus nu sigma y over e. So all we're doing is changing which one's in this spot right here. So cool. Notice once again, sigma y is 0, so this goes away. And then it's just a matter of plugging it in. So let's go ahead and do that now. Yeah, so it's going to simplify again to 1 over e multiplied by sigma z minus v, or sorry, not v, nu sigma x. So yeah, now it's just a matter of plugging it in. So let's go ahead and do that. So once again, it's 87 times 10 to the 9. That's our value of our elastic modulus. Plugging in sigma z, 160 times 10 to the 6. This is going to be minus 0.34 times 120 times 10 to the 6. Yeah, so this is going to go ahead and be your strain in the z, which if you go ahead and plug this in, you are going to get a value of 0.00137 meters. Awesome. And then once again, we're just going to use the strain formula. So this is, now we're dealing with BC since we're along the z-axis. And once again, we're solving for the change. So you're just going to take the initial length of it, multiply it by the strain we just solved for, and that's going to give you your change in length. But yeah, so delta LBC is, right, you just multiply both sides. So LBC, or the initial length, looking at it, you should notice it's just 75 millimeters, right? Because this is the length of our BC side. So 75 mm, converting that to meters, is going to be 0.075 meters. Multiplied by our strain in the z is 0.00137. And when you do that, you're going to get a value equal to 1.0275 times 10 to the minus 4 meters. And then, obviously, once again, I want to convert this into millimeters just to make it a little nicer. It's going to be 0.1028 millimeters. Awesome. So we have delta LBC right here, or the change in length of side BC. So this was what they wanted in part B. Cool. So now we have the change in length A, or change in length for part A and part B. And now part C is a little bit more complicated, but not too complicated. Now what we're going to be solving for is the change in length of our diagonal AC. So we're finding the change in length here. Now, how are we going to do this? So the first thing that you need to recognize, right, is the change in length. Let me move over here a bit. Actually, I'm gonna do it up here just because I have room. So keep in mind this is C, and what we're trying to find is the change in length of diagonal AC. So how are we going to do that? So we obviously know change in length, right, is L final. We'll call it LFAC, right? The final length of AC minus the initial length. I'll call it LIAC. So this is what we need to find, these two values. Now, the easy thing to start off with is the initial length of AC. So how can we solve for that? So keep in mind, we know, right, we're going to use a little bit of Pythagorean theorem here. We know that this length, right, this right here is AC, and it's going to form a right triangle. So if I redraw this, let me draw it like, I'll just draw it like this. So it's going to be something like that. And if we call this A, call this C, and call this B, this is LAC. And then we know AB, right, which is right here, which is 100 millimeters, right, this side right here. And we know BC, which is 75. So it's really just using Pythagorean theorem to solve for this. So this is the initial length, right, since these are the initial lengths of AB and BC, right? This is before any, any stress or any load is applied. So we can solve for it using a squared plus b squared equals c squared. So in this case, c is our hypotenuse, which is LAC. So really this should tell you is L, we'll call it IAC, once again, the initial, is equal to the square root of LAB squared plus LAC squared. So really we just want to plug them in. So let's go ahead and do that. So this is going to be the square root of LAB, which was 100 squared plus 75 squared. And then when you do this, you're just going to get LIAC, or the initial length of our diagonal, is 125 millimeters. That's awesome. Okay, cool. So now we have the first part, right? This LIAC, and now we need the final, right? Because we have the final and we have the initial. The difference between them is the change. So now what we want to do is find the change. So how do we find the change? So, or sorry, not the change, the final. So we know what the change in lengths of AB and BC are, right? If we know that, so let's just write it like this. LFAC, or the final, is going to be equal to what? It's going to be equal to the square root of LAB final squared plus this is an LAC, I apologize. This is LBC, my bad. LBC. But yeah, so this is LBC final squared. So we're just going to need these two values. So how do we find the final length of AB and the final length of BC so we can find the final length of AC? So all we did was just look at what we did in the beginning. Right, for this one, for initially, we just are going to do it for in the final state after the loads have been applied. So yeah, so how do we find it? So we know the change in lengths of each of them, right? So we know what AB is initially, right, which is this, and then we know what the change in lengths of each of them are, right? So the change in length of AB is this many millimeters. The change in length of BC is this many millimeters. So all we got to do is add them, and then we get our final length, right? So if we have the initial, the change in it, adding them will give us the final length. And then it's just plugging it in here. So let's go ahead and do that. So you're going to have LAB final is, initially it's 100 millimeters, and then it's going to change 0.0754. That gives us the final length, plus, and then I'm just going to write it down here. This is going to be 75, right? 75 millimeters is what it is initially, plus 0.10275. Make sure that's right. Or yeah, I'm just taking the more accurate value. But yeah, so this is now squared. So now we have LAB final and LBC final. And then this is going to, if you plug this in, you're getting L final of our diagonal AC, which is a value of 125.129, Yeah. Coolio. So this is your final for the diagonal in millimeters. And then, yeah, so now we have our final, which we needed, and we have our initial, which is right here. And then the change is just the difference. So you're taking this value right here and then minusing this value. So let's write that down. 125.121975 minus 125. So this should give you the change in length of our diagonal AC ending up being equal to 0.121975 millimeters. Yeah, so this right here is the change in length of the diagonal and your answer to part C. And yeah, so just a quick rundown. All you're doing is using these strain formulas based on these stress values. And it's really just a matter of plugging it in and using this formula right here for the strain, which is change in length over the initial, and then also this strain formula. And then you have to do a little bit of thinking for the last part, understanding how to solve for the diagonal, but it's not that much more complicated. But yeah, so these are going to go ahead and be your answers for A, B, and C. And yeah, so I hope you found this video useful. Hey everyone, I just wanted to say thank you for watching the video. And if you're interested in helping to support the channel and some other interesting perks, please consider becoming a channel member today. You can find more information on that by clicking the join button, which is located next to the subscribe button. And then also, if you're interested in one-on-one private tutoring from me, whether that's in engineering, physics, or math, please check the description for more information on that. But yeah, thank you and happy learning.